Hi, good morning. Good morning, everyone. Um, my name is Chenfeng Xiong. I'm an associate research professor at the Civil Environmental Engineering Department of University of Maryland College Park. First of all, it is really a great honor to be able to join this REDSA seminar series. I want to thank the session chair, Dr. Abasa, and the organizer, Dr. Domingo and Professor Moodley, for inviting me and for to be able to speak at this great seminar series about um, different aspects of big data approach. So let me start sharing the screen. So today, really, it's very interesting to join the seminar virtually with all my colleagues on this Inform Africa consortium. Um, for everybody else information, I'm currently working on transportation engineering and health related research. So that's really highly relevant to the overall scope, what I'm doing, what I'm leading for this Inform Africa's consortium on using human mobility analytics and modeling approaches to really informing the studies of disease transmissions. So without further ado, let me start introducing you guys to this exciting project. So what is human mobility? Here I'm trying to use our data to show you what's a typical day of human mobility look like in Washington, D.C. So everybody can see that in the morning, people start to traveling into the city and work and for various other activities. They may start to walk in slow mode, wandering around in red colors. Then in the afternoon peak, people start to travel out of the city with relatively faster speed, colored in green, probably in their own vehicles or transit vehicles, until late in that night, people are still in the city, doing various kind of activities until very late that night. And so this is really a quick snapshot, 30-second overview of what it looks like in terms of human mobility. But for a long time, we are not able to quantify that human mobility using different kinds of data. We were trying to understand that using travel surveys. Many of you have completed surveys yourself. It's going to be a tedious questionnaire asking you to recall your travel itinerary in the past one day or several days, which is quite cumbersome, costly, and you can only collect such small sample size in terms of travel surveys. But nowadays, with a lot of emerging information sources, technology advances such as smartphones, location-based services such as cellular towers, global positioning system or GPS, and even nowadays with our own smartphone, we could use a lot of location-enabled apps, including navigational apps, Google Map, and Apple Map, and all other apps that'll pin your locations from time to time. So all of these emerging technology are becoming our new data sources to understand human mobility. For instance, if you have been traveling using Google Map from your home to your work this morning, most likely you will become one of the samples in our data set, so that we understand collectively all the travels of all the samples in this data set. So what does this mobile device location data set look like? So this slides show you a history of our mobility data based on mobile device location databases. So starting from 1 or 2 decades ago, transportation researchers have started using cell phone data to evaluate human mobility. So that data obviously would be coarse, have to be anchored to a lot of the cellular towers across the country. So we actually do not have the absolute accurate information about location, but rather some proxies based on cellular towers. Then later on, vehicles, even someone like drivers would be equipped with global positioning system, GPS devices. And in-vehicle GPSs, these data sources become more accurate. It can pin to latitude and longitude level of detail and about second by second accuracy, fidelity, vehicles information can be tracked. But the downside would again be the sample size. Only a small percentage of individuals are really using those GPS devices. Then finally, we come to the era of location-based service, or LBS. So this data set is, again, based on smartphone-based GPS technologies. That'll give us the best coverage. As you can see from the visualization of the left-hand side corner figure, we have the highest coverage, and also it doesn't only reflect vehicle-based travel, it covers all kinds of travel that each of the smartphone user is taking every single day. And collectively, we're talking about 60% plus sampling rate in the United States. For some other countries, we do have international coverage, and the sampling rate would vary, but still it's going to be much higher than a typical survey or GPS-based study can achieve. Then several other advantages of the location-based service data for human mobility analysis would include the continuous observation. We can model and analyze one single individual along the way and depict his or her behavior changes. For instance, what's the COVID-19 impact on this person's mobility can be quantified through this continuous observation. Then it has high location accuracy compared to cellular data. It has high sighting frequency compared to survey data. And eventually, this data can be made available in near real time. In some cases, we want to have that feature. So here I'm just giving one example of our analysis. With all those location-based service data, we still need to have the big data analytics to be able to depict human mobility measurements. We were given a lot of the location points, right? According to this figure at the bottom, we're having a lot of the anonymized latitude, longitudes, and timestamps. How are we going to derive useful human mobility information? So here we are using big data, data mining, artificial intelligence technologies to depict travels from those location points. This is one illustrative example. Essentially, what you observe from the data would be a bunch of location points, but based on the aggregation of those points, we try to cluster their activity centers. It could be home, it could be different transportation facilities such as airports, bus stations, train stations. It could also be some other activity locations such as work, restaurant, etc. So, and then together, all the location points in between two activity centers naturally becomes the travels. So here in the example, we have clustered their starting points origin, then the airport location, the arrival airport location, and their final destination. Then based on analytics and machine learning, using different feature engineering processes, including speed profile, the adjacency and various features of the network, multimodal information, train stops, airports information, we also get to learn what kind of travel it may be. And this is most likely to be a driving trip from the origin to the airports. Then air travels from Dallas-Fort Worth International Airports to Denver International Airports. Then finally, the person would travel to their final destination, again, by driving or car modes. So this is one long distance tour example based on the location-based service data. And we also try to link this mobility information to answer various public health related questions. An obvious question that's relevant to this Inform Africa research project is to link the mobility trends to the COVID-19 pandemic. Here, we have published one paper in the Proceedings of the National Academy of Sciences, or PNAS. If you're interested in this paper, you can go find a publication online. In a nutshell, we have linked our mobility data. In this case, we measured the number of travels going into each county from long distance from other counties. Using that population inflow mobility trend, we try to understand and link that information to the COVID-19 confirmed cases in each destination county over the first several months of the first wave of the pandemic. So overall, we find the number one, all the mobility travels, especially the mobility inflow for each county, has dropped by 35%. But that number recovered very rapidly, especially after the US enters the reopening stage. By the way, this study is only analyzed for the US counties. Then, based on such data and the linkage between the mobility and the COVID-19, we also did a structural equation panel data model to quantify the relationship between population inflow mobility and the number of confirmed cases each day in each county. And we find a positive and very statistically strong, significant relationship between mobility and the number of infections. And we also find that relationship is increasingly stronger, is getting increasingly stronger, especially when the US entered the travel season during the summertime. And this is again corroborated later on that year during the Christmas travel season as well. And using such model, we are also able to predict, again, the Omicron surge in 2021. We are currently also studying this new data set based on vaccination records and try to understand and quantify this even more complex triangular relationship between vaccination, mobility, and the infectious diseases. So this is one of our latest research pieces that's relevant. Then most relevant to this project is really to bring this analysis to South Africa and also Nigeria, the two countries that we aimed for this Inform Africa Consortium, as well as other African countries and international countries. We do have the good data coverage. We're right now doing the data analytics technology transfer so that in the short-term future, hopefully we can come up with this day-to-day mobility measures. And we also do plan to work with our data hub partners to be able to operate and maintain web-based tools so all of the users that are interested in this mobility research can leverage. Okay, so that's our aim one. Then in this project, we also have our aim two, which is a little bit more ambitious. We're trying to build what we call a digital twin of human mobility. In other words, a digital version of the transportation system. So in this world, we're trying to use data-driven approach and deep learning algorithms, artificial intelligence, to reconstruct the entire population using a population synthesizer and try to learn different aspects of their travel, including their daily travel itinerary, where do they travel to, they have daily travel itinerary, and also they have their once in a week or seasonal travel trends as well. Then for each travel itinerary, we also try to predict their departure time of each travel, the modes they choose to fulfill their travels. Do they choose to drive or do they choose to use public transportation systems? Then finally, they may have the route choice. Do they pick multiple transfers at train stations or do they prefer nonstop? And if they do drive, what kind of routes do they choose? So all of these becomes different components of the digital twin model of our human mobility. So I don't want to waste too much time to go into details, but right now we are at the demonstration stage. We have constructed a digital twin of one county in the United States using Montgomery County, Maryland as an example. Then we have constructed visualization as well so people could see different scenarios the digital twin model can simulate. So here we are visualizing our commute scenario. A lot of people commuting to DC to work in the morning. Again, we are visualizing only 1% of our agents or population synthesizers. We use green color to label commute, then yellow color are those non-commute travels. During the middle of the day, more non-commute are occurring in the DC and suburban areas, and during PM peak hours, we see more commute travels going back to their home in the suburban areas. We even see someone commute from Baltimore even longer distance, maybe via air, that's coming into town. So this will essentially enable us to do a lot of the predictions and to answer the what if questions for policy changes. For example, if we want to analyze mobility restriction policy in Southern Africa, for example, we could use this digital twin model to predict what's the human mobility response to such policy changes. Okay, so then finally we have our aim 3. Based on all of these good and accurate and disaggregate individual level mobility measures, how can we also better inform the public health decision makers or some practitioners that's working in the health analysis, health data analytics framework field. So here we propose to come up with a novel measurement based on our detailed location information. We try to design a space-time buffer for each traveler. If you are traveling by air, we try to design a buffer of maybe 30 minutes or 100 feet space buffer and 30-minute time buffer to quantify how many other travelers have interacting with you. And by looking at each traveler that's close enough to the target traveler I, we can see the origin of this traveler, and are they from a place with a lot of confirmed cases, or they are coming from a relatively safer counties, so that essentially we can come up with a measurement of COVID-19 exposure risk based on this fairly accurate measurement. Then how to calibrate such a measure? We are thinking of collaborating with agencies that has the capability to do Bluetooth contact tracing. In this case, United States have such data from, for example, the Department of Health in the District of Columbia. The capital city, has set up this DC CAN alert system based on Bluetooth contact tracing. For instance, this figure showcases that, by different day of the week and time of day, when would be the most critical time that more people are interacting with each other. And it seems like during Sunday and Saturday afternoons, 3 to 5 p.m., we observe the most personal contact. On average, there are 14 contacts each person would be making. So this one becomes our naturally good data source to calibrate our novel measure. So essentially we are able to apply this measurement to a lot of the other places that cannot afford such a costly Bluetooth contact tracing platform, maybe in Nigeria or Southern Africa. So we still can enable our cheaper version of the mobility data to fulfill such contact tracing purpose. And ultimately, we can link that novel measurement to a epidemiology compartmental model, which will be built by our collaborators in the University of Maryland, Baltimore campus School of Medicine. Okay, so, to summarize, we're so excited to be able to working with this brilliant group, Inform Africa Consortium, on our specific aims. Number one, we would like to do the data analytics, understanding human mobility at individual level, and quantify that to be able to help us understand, for example, the behavior responses when we do have the movement restrictions, and how would mobility, again, lead to various COVID-19 related virus transmissions, as well as other infectious diseases as well. Then the specific aim 2 will determine whether movements restrictions, will result in distinct mobility patterns using different mobility modeling technologies, what we call digital twin modeling method. Then specific aim 3 would quantify the expected contribution of mobility patterns to infectious diseases dynamics using that integrated mobility and epidemiology model. Of course, there are also other important research needs or research thrusts we want to explore, including the problem. I know the Red Symposium has a specific aim on ethics. We're also in line with the goal to protect privacy, addressing those sensitive information properly. Right now, we are practicing all the analytics are cloud-based, so that we minimize the risk of data leakage. Then we white label all the information about home location, work location, so that those detailed information will not be reflected in any of our traces. Of course, we are happy to learn from the consortium, from the symposium seminar participants on what are the best practices we should implement along the way, and we have to have that discussion. Then sample representation as well, how the population is represented in our data samples, and then are we able to capture all their travels, or are we missing some part of the travels? Should be carefully studied, making sure, and as relevant to the number 3 point as well, we have a proper way to address the potential bias for the systematic data-driven approach. Essentially, those underrepresented samples, for instance, those neighborhoods who are, less penetrated by the smartphone technology, should receive a higher weight in our final model. So those are in the consideration. Well, without further ado, I hope this project will get you equally excited as I am. Now we are merely in our year 1 of this exciting 5-year project. If you have any questions or any comments, I'm happy to interact with you, and I'm phone and email reachable at this address. Again, thank you all for your time and interests, and looking forward to our further communications over this Inform Africa Consortium work. Thank you.